Hello class, in this video we'll talk about hydrates and then we'll talk about combustion analysis. Both of these topics are based on molecular formulas and empirical formulas. So if you don't have those that information fresh in your mind, maybe you should review the previous video, which is video number 7, I believe. So hydrates. What are hydrates? Here is a definition. So these things contain water in their chemical formula. All right. Now the water is just bonded to the substance. It is not actually part of the chemical makeup of the substance. It is just bonded to it. For example, CuSO4 dot 3H2, CaCl2 dot 2H2O, both of these are hydrates. Okay, so again, the dot there simply means that the water is bonded to the copper sulfate or copper 2 sulfate or the calcium chloride. Okay, now we use hydrates to keep things dry. Okay, in their anhydrous forms, because hydrates in their anhydrous form love water, so they are used to absorb water from things or from the air. Now, any substance that can absorb water from the air is said to be hygroscopic. Hygroscopic with a G, not hydroscopic. Okay, with a D. So hygroscopic with a G. All right. How do we name hydrates? Hydrates are named as follows. We use the name of the anhydrous form, and then we add a prefix, and then we add the word hydrates. Hydrate. Okay. If it's a hydrogen, if it's a deuterium, which is a hydrogen with 2 protons, we say deuterate instead. So the prefixes are as usual, mono, di, tri, etc. For example, this would be copper 2 sulfate trihydrate. Okay, this would be calcium chloride dihydrate. Okay, easy enough. How do we get the formula of a hydrate? The formula of a hydrate is always written as the anhydrous form dot X H2O. Now X is we call it a coefficient. So in this case here, this 3 here is a coefficient, and this 2 here is a coefficient. These coefficients represent the molar ratios of H2O to the anhydrous form. Okay. So for example, in the copper 2 sulfate trihydrate, there are 3 moles of water per mole of copper sulfate. Okay, so there are 3 moles of water attached, or you can say also 3 molecules of water attached to every molecule, if I may say, of copper 2 sulfate, even though there is no such thing as a molecule of copper sulfate, remember, because it's an ionic substance, it is a formula unit. Okay, so I should technically say 3 molecules of water attached per formula unit of copper 2 sulfate. So that's it for hydrates. Let's move on to combustion analysis. Combustion analysis is pretty similar to molecular formulas and empirical formulas. So if you understood those 2 things, then combustion analysis should be very easy. Okay. Now, a combustion, as you probably remember for chemistry 201, is when a substance is burned in the presence of oxygen, because nothing can burn without the presence of oxygen. So we could imagine compound X reacting with oxygen to produce water and carbon dioxide. That would be an example of combustion analysis. Now, water and carbon dioxide are going to be key in what we are going to be doing in the next few slides. So keep them in mind. This is a diagram that shows how how combustion analysis is done, but you don't have to worry about knowing the details of it. So in general, we will be dealing with compounds containing hydrogen and carbon and oxygen, and sometimes nitrogen. Okay, we will rarely go outside of those 4 elements. We determine, in order to get the formula, obviously we need to get the percent compositions usually, and then go from there to the empirical formula, and maybe to the molecular formula if we have the molar masses. How do we determine the amount of carbon? It is determined by the amount of CO2 produced. If you guys remember this, we said that we will assume that we have a compound that when burned produces carbon dioxide and water. So the amount of carbon is determined from the CO2, the amount of hydrogen is determined from water, and the amount of oxygen is determined from the difference between the mass of the sample and the mass of the carbon added to the mass of hydrogen. Okay. Now let's take a look at let's take a look at an example. Let's say we have a sample of 95.6 grams of this substance, the molar mass of which is given 156 grams per mole. And this is burned, and we produce 269 milligrams of carbon dioxide and 110 milligrams of water. Be careful about the units here. It's milligrams for both carbon dioxide and water. Milligrams, which means 10 to the negative 3. How do we get the formula of Manthal from this data? Well, here's how. It's pretty easy. First, we get the mass of carbon. We said we get the mass of carbon from the mass of carbon dioxide. You should know that for every molecule of carbon dioxide, there is one carbon atom. So the number of moles of carbon dioxide is equal to the number of moles of carbon atoms. Since we have the mass of carbon dioxide and we can determine the molar mass of carbon dioxide, we can determine the number of moles of carbon dioxide, which is the same as the number of moles of carbon. And then we get the mass of carbon by multiplying the number of moles that we got by the molar mass of carbon, which is 12. Okay. Then we tackle hydrogen. We get the amount of hydrogen from the water. But in this case, the number of moles of hydrogen is twice the number of moles of water. Do you know why? If you don't, let's talk about it in class. So the number of moles of hydrogen is twice mass of water over molar mass of water. Now, mass of water over molar mass of water, that's the number of moles of water. Okay? So we do that, and here we go. We get the number of moles of hydrogen. The mass of hydrogen is going to be the number of moles that we just got times the molar mass of hydrogen, which is 1. So now we have the mass of hydrogen. Now we have both the mass of hydrogen, and which is here, and the mass of carbon, which is here. So what do we do? How do we get the mass of oxygen now? Well, we add these two, and we subtract them, or we subtract the number we get from the mass of the sample, and whatever is left is going to be the mass of oxygen. So let's do that. This is, of course, assuming that the substance is made of only carbon, hydrogen, and oxygen. So there you go. We get the mass of oxygen. And from here, we can get the number of moles of oxygen by dividing mass over molar mass. So there you go. Molar mass of oxygen is 16. There you go. Now we have the molar mass of oxygen. Now, if you guys remember, from here, it's the exact same thing as determining empirical formulas. So we get the mole ratios by dividing the larger number of moles by the smallest one. So oxygen has the smallest number of moles, so we divide by it. So carbon over oxygen is about 10. Hydrogen over oxygen is about 20. And of course, oxygen over oxygen is 1. So our formula is C10H20. All right, so this is how we work with combustion analysis. Maybe another example. And here it says, do not round the atomic masses. So do not round. Here's a problem. We get the number of moles of carbon this way. If you don't understand, just rewind the video. Go back to the previous slides. We get the mass of carbon by multiplying by the molar mass. We do hydrogen by using water. But remember, the number of moles of hydrogen is twice the number of moles of water. And then we get the mass of hydrogen by multiplying by its molar mass. Notice that we didn't round. Instead of 1, we are using 1.008. I mean, we kind of rounded a little bit because it should be 1.0078. And then we get the number of moles of nitrogen. The number of moles of nitrogen, since we are given the mass of nitrogen right here in the problem, we just go ahead and divide by the molar mass, which is 14.007. Now, I notice I kept these numbers of moles in red for you because we will be taking their ratios. And then the mass of oxygen is going to be the difference between the different masses of the elements that we have we subtract that from the mass of the sample. So we have the mass of oxygen. Guess what we are going to do next? We determine the number of moles of oxygen. Now in red, we have the number of moles of the 4 elements. What we are going to be doing next is taking the ratios. So we will be taking the ratios, but before we do, let me just show you again the number of moles of the different elements. So we go ahead now and do the ratios. We divide the largest ones by the smallest. And can you spot the smallest one? I think I can. So right here, so nitrogen and oxygen are the smallest of the numbers. So we divide each one of these two by the nitrogen or oxygen. So carbon over one of those is 10. Hydrogen over any one of those is 12. And of course, nitrogen and oxygen, the ratios is 1. And from here, there we have the formula. Okay. Now if we calculate the molar mass from this formula, we get 162. And we were given in the problem that the molar mass is 324. Let me show you. Can you see? Can you spot it? It's right here. So we are given the molar mass in the problem. So what do we do now? We take the ratio of the molar mass that is given over the molar mass from the empirical formula, and you can see that this is 2. So we just need to go ahead and multiply everything here by 2. So this was the empirical formula, and this is the molecular formula. This is it for this video. I will see you in class.